so we're back to it. We are making our way through Gen Chem 2, and I guess we're just learning a little bit more and kind of just continuing on with thinking about how, let's say, molecules interact with each other, I guess. And just to kind of paint a picture about where we're going, I suppose, the first two chapters here are going to be a little bit conceptual. As you guys have probably figured out at this point, you know, there's not too much math that's coming out of chapters 11 and 12. They're just kind of describing the properties and the ideas, and then how we can use those concepts to kind of build new materials and all that kind of stuff, which is mostly what chapter 12 focuses on, kind of modern materials, I think is what the chapter is. It's kind of a weird inclusion, I'll be honest. But anyway, that's neither here nor there. That's just an opinion. But anyway, the idea is we're going to see these principles at work through our other courses, and that's kind of why they focus on it here. But immediately, it's also what we're going to do in the next chapter, which we'll probably get to today, is we're going to start to talk a little bit more about solutions, even though we've already talked about those quite a bit in the first semester. But then, essentially for the rest of the semester, we're going to just talk about specific properties of different types of things in solutions, what it is, different types of reactions and that kind of stuff. So all these things are going to be at work behind the scenes, but then we're going to move away from the conceptual and move into the quantitative, and, you know, working a lot more on the math and that kind of things. So the first couple of chapters are a little bit different, but then it'll take a sharp turn there around chapter 13 when we talk about reaction kinetics, and then moving into equilibrium and acids and bases and all that kind of stuff, right? But as I promised, you'll see this stuff all come up again when you guys are going through organic and biochem and all that other kind of stuff. All right, but anyway, a little bit more on the, I guess, what do I want to call it, the paperwork side of things. So I managed to get one of the videos uploaded, and I tried to do the other ones, and they failed in the same way. So I don't know. I need to go yell at somebody until something gets worked out. So I promise I have the videos. It's not just me being like, yeah, whatever, we'll get to it later. Like it's I don't know. If I had a good explanation for you guys, I'd tell you exactly what's going on. But I promise as soon as I get it all squared away, the videos will be up there, and then you guys can make sure that you fall asleep soundly at night listening to general chemistry lectures once again, right? It'll be nice and effective, and you don't have to worry about taking any sleep supplements anymore. So, but anyway, in the meantime, we'll keep going. Next week, we'll probably start to have a quiz or so. Those will be online, so just keep an eye on that. It'll be probably on chapters 11 and that kind of thing there. So take a look in the back of the book. That's usually the kind of stuff where I'd like to grab questions from, and those kind of examples from the chapter itself there too. Okay. All right. I think that's kind of all I needed to share with you guys. I think that's kind of all that I had thought about. Okay. So we'll pray, and then we'll launch back into it here. But Lord, we just thank you for another opportunity and another day. And we just thank you for another chance that we can just get up and just, you know, learn a little bit more about the world that you've set before us, Lord. And just open our eyes to the things that you would have us see, Lord. And just help us to focus on those things that you set before us, Lord. Help us not to get distracted with the world and the things around us, but rather on the things that you would have us set our eyes on, Lord. Just pray to give us the courage and the strength that we need today, and the wisdom just to make it through the day, Lord. We pray that you be the lamp unto our feet, Lord, just to guide us on the path that you'd have us walk. We just pray all these things in your name. Amen. All right. So, we had talked about solids, we had talked about liquids, and now we're going to talk a little bit about solids and kind of some of the things that go along with that, and just tie it back to the same principles that we have been all along, and just do a little bit of jogging the memory, I guess, from Gen Chem. We'll do a couple examples here at the end of the slides, just to kind of remind us of things that we saw in the first semester. But anyway, we talked about melting and crystallizing, and so when we're dealing with solids, right, we could talk about kinetic molecular theory, and that's kind of what the top part of it says there, right? That's all it's saying. It doesn't have the energy to slide past each other. Remember what we talked about with why do things why do liquids move, or what's viscosity and all these kind of things. It's just how well do these molecules interact with each other, and is there enough energy for them to start to move is what it is. Okay? Now you'll see down in the corner here we talked about fusion and crystallization, just as we talked about vaporization and crystallization, vaporization and condensation, right? So the same kind of ideas there. Melting is endothermic, freezing is exothermic. There's a gain and a release of energy as you melt or as you freeze something. Right? And I could ask you guys a question that I did previously or on Wednesday. Why? Why would melting something be endothermic? Now you guys already knew this, right? As if you take a block of ice and you put it into a pot on the stove, right? You add energy to it, it's going to melt. Why does it take energy to melt something? Yeah.
Because it's moving to a higher energy state.
Oh, sure, but where's that energy go? Yeah, Chris.
It's needed to break up the intermolecular bond.
There you go, right? Remember, when you're in a solid, you have things packed very closely together, right? Just like if I took a couple of the desks out of here, you guys would be crammed next to each other, right? And you get a little bit uncomfortable, you can't move around as much, you can't get up. If you do have to get up and leave in the middle of class, right, you got to do that awkward thing, like, do you walk in front of them, or do you show them the butt while you walk by them, right? You know what I'm talking about, like when you're at the movie theater, right? That awkward kind of way of moving past each other, okay? It's the same thing that's happening here, right? You have to add energy to overcome the interactions that you have with the things around you. That's all we're talking about. Whether it's from solid to liquid, liquid to gas, right? It's going to take energy to break apart and help those molecules move past each other, right? And so the opposite then has to be true. If we're going from a liquid into a solid, then we start to create those intermolecular forces, right? We release energy whenever we make a bond, if you want to think about it in that way. Now, what you guys might be thinking is, well, there's different types of bonds, Dr. H, and you're absolutely right with that. We talked about covalent bonding and ionic bonding, all the stuff that goes along with that. But if you think about it, intermolecular force is just basically just a kind of weaker bond, right? Things are interacting with each other. But you guys already knew that, right? Right? Yes, thank you. All right. Okay? So let's think about this for just a quick second here. Now let's take it a little bit, if you guys don't know me, I love to overanalyze things. Like some of my favorite videos to watch on YouTube is where they go like through all the movies and they point out all the mistakes and stuff, right? It's because I love to be critical of things. No, that's not it, right? I just like to analyze stuff is what it is. But so let's think about this for just a second here. What makes a bond? Yeah?
Electrons?
Electrons do, right? What is involved in intermolecular forces?
Electrons?
You guys get what I'm saying? So all I'm saying is it's just how electrons interacting with each other. That's all it is. So it should make logical sense then. If you're making a covalent bond, there's a release of energy. As you start to have these dispersion forces or hydrogen bonds or any of these intermolecular forces build up, there's going to be a release of energy with that also. Okay? That's all we're saying with it. Cool. All right, so there that is. I think I've kind of exhausted that. All right. Something we haven't really talked about too much is the idea of sublimation and deposition. That's where you go directly from a solid into a gas or a gas back into a solid. I think the common examples that they tend to do with these two phase changes are they tend to show iodine as a good example of sublimation. So if you get elemental iodine, it's these beautiful purple crystals, right? And even at room temperature, you'll see them basically, it looks like the liquid is, the crystals are evaporating, and you'll start to see them crystallize on the side of the jar that they're in and all these kind of things, right? There's a million examples of this on YouTube too. And that's fine. There's a little bit of a argument, I guess, in the scientific realm about whether iodine actually sublimes or not. But so maybe a better example of sublimation is dry ice. Now all of you guys are probably familiar with dry ice, right? So if you take carbon dioxide and you turn it, right, and you compress it and you cool it down or whatever you need to do, it'll turn into a solid CO2, right? And when you leave that out on the bench top, it's not going to turn into liquid CO2. Liquid CO2 can't really exist at ambient pressure, so it'll immediately turn into CO2 gas is what it is, right? So that's probably the better example for what we can see with sublimation. Deposition, I really don't have a good example to talk to you guys about, right? It's just the opposite of what happens with sublimation. I know the book talks a little bit, hang on just a second. I know the book talks a little bit about how they plate certain metals onto different electronics and things like that. And that's fine, but I don't know, that's a little bit esoteric, right? That's not really something that we see every day, right? That we might be able to visualize. So sorry, I don't have a good example of deposition. If you guys come up with something, let me know. Yeah, what's up?
So why can't CO2 exist in the liquid state under normal conditions?
Ah, that's a good question, isn't it? That's a good quiz question. Yeah. So remember, everything's a balance of how much energy is around, right? For something to be in a liquid, you have to have the right amount. If you think about it, there has to be the right amount of energy to be able to favor the formation of the intermolecular forces, so that you can be close enough together to interact and form a liquid, but not too close together that you form a solid, you know, all these kind of things with it, right? So what I'm saying, it's a complex question. I wouldn't ask you guys that for a quiz. There's no good answer. Well, there are good answers, but it's a little bit, I don't want you guys to write me a treatise on this, right? It would take quite a few pages, and I don't want to read that much, right? I'll just be honest. Like, oh, they wrote 3 pages, yeah, it looks good, A's, right? But anyway, so there's a lot of different factors that come into play with this, and I'll talk a little bit about it in the next, is it the next chapter? There's some slides coming up that I mentioned this a little bit. I think it's either in the next chapter or coming up here soon. And so we'll see there's a lot of different kind of factors at play, which might be the best answer for you, right? Okay, so there's that. And just as we talked about with exothermic and endothermic, I could go back and ask you guys the same question as to why is sublimation endothermic and why is deposition exothermic, right? You guys would come up with some kind of the same answer there as to dealing with intermolecular forces and how well the molecules interact. More questions? Oh, geez, aren't no.
The heck is the deal with plasma?
What do you mean?
It has
Like-
one connection, the others all have 2.
Yeah, it's just a high energy state where you have ions around in the gaseous form.
So it's ionized gas.
Yes.
Then why is it considered a different state?
Because when we're talking of, let's see here. Why would it be considered a different state? I guess because it would have it has different properties that are unique from the other ones, from the other states, might be the best example for that, right?
Does it kind of have the same like mechanism of change from gas to plasma of like it requires it? I guess if it's ionized.
Yeah, everything requires an input of energy, yeah.
Okay. Thank you.
Yep. I know that answered your question 100%, so you're welcome. All right, so just as a couple of examples here, right, if I could ask you the question about explain the trend in melting point or boiling point for these compounds here, right? A very typical question that you see at the end of the chapter, right? So why would oxygen have a boiling point of negative 183 and bromine have a boiling point of 60 degrees Celsius, right? And the way you approach that type of question, the way you start to answer that type of question, is by looking at what intermolecular forces are present in those molecules, okay? Because if we're relating everything to these forces in this chapter, then that would be the way to approach it for these types of questions also, right? So, and we'll do an example at the end of I've got an example for you guys at the end of this that we can kind of go through with that, right? But here what you'd see is that these are all non-polar, right? What do we mean by non-polar? Kayla, give me an answer. What's a non-polar?
It's an equal pool.
An equal pull of what?
The negative and positive charges.
Yeah, right? So there's an equal tug of war going on, right? The tug of war of what? How do we know which one is a stronger tug of war or not? What am I talking about with this? What's the principle behind the scenes? One of these important periodic trends. What's that?
Electronegativity.
Perfect, electronegativity, right? So when we're talking about polarity, you guys have to assess the electronegativity of the individual atoms that are part of the molecule, right? Because if one side wins the tug of war, then there's going to be a permanent partial positive and a permanent partial negative. Got it? You guys catch that key word that I'm just using there? It's what? Permanent, right? Permanent and partial, right? Permanent and partial charges indicate a dipole, right? Two poles, it's a polar molecule. With me on that one? Right, so if we don't have anyone who wins the tug of war, oxygen can't tug on oxygen more, right? Then all we have to deal with is the dispersion forces or the London forces. And that's all dependent on what?
The number of electrons or the radius of the?
Yeah, kind of both, yeah. Right, so we would say, to simplify, we would say the number of electrons. How big the electron cloud is, right? It might be a slightly different way of saying that. You guys with me on this?
Vaguely.
Vaguely, that's okay. There's actually something else that's going on, and we'll talk about it at the end. So if you have a nonpolar molecule, the first thing to assess is looking at how many electrons there are, okay? And then we'll talk about how geometry has an impact on this also, okay? Yeah, what's up?
Can I just give one little recap how to find if it's non-polar or polar?
Okay, sure, of course. So how do we assess if a molecule is polar or not? There's two things you need to know. The first, you guys already told me, is electronegativity, right? And then as the answer was given, it's, well, is one side of it winning the tug of war? So we need to know electronegativity, and then what's the other very important thing we need to pay attention to? Yeah.
Molecular geometry.
Aha, the geometry of things, okay? Because if it's just one atom bound to another, right, we can pull against each other. But is everything a linear molecule? No, it's not, right? We have linear, and we have trigonal planar, and we have tetrahedral, and trigonal bipyramidal, octahedral, right? All these different geometries in there. And so if you guys remember, we talked a little about vector addition, right? Or qualitatively, we talked about vector addition in the Gen Chem, right? And how if you have things pulling in different directions, it's the sum of those forces, right? You guys remember that? Little bit? 3 of you guys, 4, 5? Okay, now you guys are just nodding, like, yeah, if I nod, he'll just keep talking. Right? But don't forget, it's two things to determine whether you have a nonpolar molecule. Electronegativity, and then don't forget to look at the geometry. If you just assume everything's planar, that's a bad assumption, okay? You're probably gonna start to get things wrong with that, okay? Do you guys remember how to draw the different geometries? Sure, okay. I'm very confident, sure, okay. Okay, but that'll be also something important to remember as you guys move forward too, okay? But good question with that one. All right, so at the other end of things, once you have polar molecules, this might be your best answer. There's a lot of different factors at play here, right? The geometry, how strong the individual positives and negatives are, right? If you have a bigger dipole or not, this kind of thing, okay? So it's not quite as simple to compare just a list of polar molecules. Sometimes you can do it, right? There's some factors there's some lists that are a little bit easier to pull out the individual factors for, but it's not always that simple. The best example might be, water is such an anomaly in terms of its boiling point and freezing point and that kind of thing, right? It's a tiny molecule with a huge boiling point and huge enthalpies of vaporization, right? So it's unique in the way it works there, right? So when you're given a list like this, you have to kind of assess everything on an individual basis, right? If I ask you guys a question, right, I have to make sure that there's a reasonable answer that you guys can draw out of it, right? If I ask you guys a vague question, then how can I really, assess whether you guys understand it or not, right? So when I ask you guys a list of, hey, rank the following in increasing boiling point or something like that, you guys should be able to say, okay, well, this one has hydrogen bonding, this one doesn't, right? So this one's probably gonna have the highest boiling point, right? That kind of assessment that comes with it. Does that make sense? What I'm saying is there's always gonna be an obvious answer. I'm not gonna try and trick you guys, I promise. What's up?
So you're saying hydrogen bonding results in the highest boiling point?
That's the way the book presents it. It's a fair assessment for what we're dealing with.
Okay, so at what point do the London or dipole bonding overtake hydrogen?
Yep. I get to give my favorite answer. You know what it is?
wait till?
It depends. You keep asking these, it's good, they're good questions, I don't mean to discourage you, but what I mean is, if you allow me to ramble for just a second, there's a tendency for students to want a black and white answer. I get it, right? I get it. I know why you guys are asking. I don't want to discourage the questions. But what I'm saying is there is no answer like that. I cannot tell you once it hits 70 electrons, then hydrogen bonding doesn't matter. It just doesn't work in that way, right? So that's why I'm saying I have to give you some kind of discrete analysis for whatever list that I give you, right? For you guys to be able to come up with an answer. Otherwise, it's just vague and there's a lot of things going on behind the scenes, right? Okay, cool. And then one other thing that we didn't mention too much last semester, but when we're talking about melting and intermolecular forces and all that kind of stuff, something to pay attention to is the charge on the anions themselves. So if we do have an ionic compound, right, and we've got a series of like sodium chloride, bromide, and iodide there, each one of those ions either has a +1 or a -1 charge, okay? If I increase the charge, okay, to -2 or +2, it's going to be harder for these things to melt, right? And that's just a pure argument of Coulombic attraction. If I'm a +3, right, I have a bigger positive charge, it's going to be harder to take a minus away from me. You guys get what I'm saying? Right? Whereas if I have just a +1, it's a little bit simpler. So take a look at the charges of the ions that are involved with the molecules that you guys are dealing with. Okay? Does that mean that radius isn't at play? No. Okay, if I changed from sodium chloride to potassium chloride, right, we would also affect the melting point. Because we have a larger radius and that has an implication with it also there. Okay? So the same kind of principles are at play, the size of the molecule, if you want to think about that, but also the charge is going to be important when you're dealing with ionic compounds. Okay? All right.
Excuse me.
Yeah.
Is that, so that's because iodine is more electronegative? And so, or, I'm lost, why is the boiling point?
Has a bigger radius.
Why is it smaller in this case? Is that what you're asking?
Why is it, what's the trend there? Like, it goes down.
Yeah, it has to deal with size. So if you think about it, like iodine is a huge, huge, huge molecule,
Okay.
right? And so it just, packing a sphere, right? So atoms are spheres, right? Have you guys ever gone to Walmart, right? They have that crate of like the kickballs or inflatable, you know, like beach ball, right? And it's just stacked up in a crate, right? There's a lot of empty space, right? Spheres are not very good at maximizing space, right? Which is why raindrops, you know, and you know, spherical drops are the volume to surface area arguments, right? And so if the bigger that sphere, the less efficient the packing can become. Or I should be careful and say the bigger the mismatch in the size of the spheres. You'll notice that sodium doesn't change its size, right? It's always going to be the same through all of these. And so it becomes a mismatch in the size of the anion versus the cation, right? But if I started to change that from sodium iodide to like cesium iodide, which is a bigger radius cation, then it'd be a little bit more efficient at the packing is what it is, okay?
Okay.
What's that?
So would cesium iodide have I'm assuming it would have a much higher boiling point then?
You know, it should. I don't know it off the top of my head. But I think it should I think it'll probably be a lower one, to be honest.
A lower boiling. But so then
somebody can look it up real quick.
would cesium?
If you guys are interested in seeing if I'm, you know, how right and wrong I am. I'm gonna go with lower, but go ahead.
And then would cesium chloride be?
Yeah, there you go back to that argument about mismatch in size, right?
Okay.
So
So you're gonna have a lower boiling point, definitely.
I think so for that one. What the?
Cesium iodide is 1,280.
Okay, I was way wrong.
Celsius.
There we go. So we've got the argument of increased Coulombic attraction there, or the increase in the amount of electrons. Fantastic. All right. So real quick then, how do we start to put all this stuff together? Okay. So here's something we talked about last semester. All right. So these heating diagrams. So if we take everything that we've learned here and start to put them into something a little bit more numerical, right? And I ask the question, how much energy does it take, right, to heat 100 grams of ice from -20 all the way to 120 degrees Celsius, right? Each of the steps on this graph here represent a specific transition or a specific increase in energy, okay? And so the horizontal lines there in blue, these represent your phase transitions. Now here's something that's important to remember. When you're talking about a solid to liquid, right, if I'm melting something, that happens at a constant temperature, okay? That happens at a constant temperature. It's isothermal, if I think is what the book starts to call it, right? And so the melting and then the boiling is at a constant temperature. So when I take water to 32 degrees Fahrenheit or 0 degrees Celsius, it melts, okay? But think about this for just a second. So I'm telling you, ice melts at 0 degrees Celsius, and you guys are like, yep, you got it. What else happens to water at 0 degrees Celsius? It freezes. Do you guys catch what I'm saying with this? So if I have water at 0 degrees Celsius, it is melting and freezing at the same time. You guys got me on this?
Kind of like when you take a beer bottle and you get it really cold to where it's at 0, but it's not frozen yet, then you pound it and it suddenly turns to ice and it blows the cap off, and then you gotta wait for it to melt so you can drink it.
Nope, that's nothing like that. Right? That's something else. That's a super cool liquid, but that's in the next. I think the next set of slides. Okay. But here's something that we didn't talk about in the first semester. This idea of what's known as an equilibrium. You guys have probably heard this term before, and you kind of see it thrown around in different places, and you see it in biology and all these kind of things. But equilibrium in chemistry just means moving from one side of an equation to the other, right? That's really what it's kind of going to mean for us. Now, of course, it's going to get a little bit more complex than that. But essentially, essentially what I'm saying is, at some point, let me do it in blue so that it kind of sticks together here. At some point, we have a liquid which is turning into a, try this one more time. Okay, we've got a solid which is turning into a liquid, right? And at the same time, the liquid is going back into a solid. And so what you'll start to see is I'm going to start to bring these ideas of this equilibrium a little bit more until we get to chapter 14, and then we'll start to put some numbers with it, okay? But if you want to, so for the moment you're saying there's some kind of balance that happens in this reaction. That's all it really comes down to. Does that make sense? So the question then, when you see this type of question in the book, you have to pay attention to which direction we're going. You guys catch what I mean with that? Which way are we following the arrows? If I'm adding energy into ice, what does it mean I'm doing? I want to do what? Go from a solid to a liquid. You guys with me on that? But if I'm cooling water down, then we're going the other direction. Make sense? Right? At the red sloped lines here, that's where I'm taking liquid water and I'm starting to heat it up. So the phase is constant, right, at those red lines there, right? I'm taking water and I'm heating it up, right? So you guys have a pot of spaghetti water, you put it on your stove, right? Eventually it gets to the boiling point and then there's another phase transition. But in the meantime, you're just adding energy into that water. Does that make sense? Right? Yeah.
This is a little bit off topic, but I'm just curious.
Are you sure? It's not about spaghetti water?
It is. When you're warming up a pot of water,
Yeah.
does it, like ideally, it would all start to boil at one temperature all at once and all the bonds start breaking at once?
In an ideal world, yes.
So in reality though, do certain parts of the water reach that boiling point quicker than others?
I think they don't reach the boiling point, but they turn into a vapor, I would say, right? But you guys know this, right? So if you have a steaming cup of coffee, right, what's the steam? There's water vapor coming out of it, right? Is your coffee boiling in your mug? No, right? So there's other things that play with this, and that's why I say, if you have a perfect universe where nothing else is going on, you just have water, right, in a completely inert atmosphere, whatever you want to say, then I would say your statement is true. But in reality, there's other things at play.
Yeah.
So and we're going to answer that question in, I think it's like chapter 18 or something like that, where we talk about spontaneous reactions. Okay, so what we'll learn, and we'll start to, there's not just energy, or excuse me, there's not just enthalpy, that's a measure of the energy of a system, there's other measures that factor into this. Okay, and so we'll talk about those as we go through.
Okay.
Yeah.
So what's the deal with how, when ice is under a greater amount of pressure, it has a tendency to turn back into water?
Not a tendency, it does turn back into liquid water, yes.
Okay.
Yeah.
Why?
Yeah, that's a great question. So the question was why, water is we've been studying water for centuries at this point, right? And there's still active research that's going on with it through today. And I'm not talking about, some guys just curious and looking, like this is like people at major research institutes looking at how water behaves. So real quick, just to kind of put into point, how many different crystalline forms of ice exist? You guys might say, 2, Dr. H. I don't want to, there's about 17 different forms of ice, right? And we don't see them all on Earth, right? Because these exist at different pressures and at different temperatures. There was recently, it was a publication, I believe, in Science or Nature, one of the 2 top journals, where they found ice trapped within a diamond. It was one of these new forms of ice that had been discovered on Earth, right? They'd never seen it before here. Now, the reason why this happens is, now this question you guys can answer. What's the dominant intermolecular force in something like water and H2O? Go ahead.
Hydrogen bond.
Hydrogen bonding, right? Now, what we haven't talked about, because it's a little bit advanced, is that hydrogen bonding is directional, right? The hydrogens have to be pointing at the atom that they're going to interact with, okay? And much like if you're aiming something, if you're a little bit off, right, you're gonna miss just a little bit, right? And it's gonna change how those bonds get formed. So the point being this, ice can arrange itself and aim itself a little bit differently and start to form different forms, water can aim itself and start to form different forms of ice. But you guys also know what? If I take ice and I put it into water, what happens?
Melts.
Well, it will do that, but what else?
Like cracks.
That's part of the melting process, right? You're disrupting the lattice. Ice and water, does it sink or float?
Flow.
Why?
Because it's lower density.
Lower density, what does that mean? There's a lot of what in ice then? There's a lot of open space. There's a lot of empty space. You guys got it? So what happens when you put pressure on something? What are you physically doing to the molecules when you put pressure on something?
You're moving them closer together.
You're pushing them closer together, right? And if I'm ice and there's a lot of open space, that means I can squish this together. And if I squish that together, I disrupt the hydrogen bonding, which keeps it in its solid form. And so it melts back into liquid, is what it is, right? That's all it comes down to. You're putting pressure on something. Now, that is something that's unique to water. There's not too many other molecules that exist where that happens. Pretty much everything else, when you put it under pressure, it'll turn back into a solid rather than go into a liquid, okay?
So, my brain is having,
Fair enough.
Still a little confused at why that would mean water can form, or ice could form on the inside of a diamond, because I would think a diamond would form under pressure.
Exactly, right, good point. So if there's at a certain pressure, right, it forms the hydrogens are aiming in a different way that can still allow it to form a solid. That's what it comes down. That's why I said there's these like 17 different forms of ice. It depends on the temperature and the pressure at which these things start to align to form the ice itself. Okay? And so there is actually, here's your answer to this. There's things called phase diagrams, right? And phase diagrams are just pressure versus temperature, and it tells us what phases exist at those individual points there, right? And so this is a phase diagram for just something generic, right? This isn't water, right? But all it shows us is the solid, the liquid, and the gas, right? And the lines here just represent the change in between the two states, okay? So as I cross over one of those lines, if I'm here from a solid directly into a gas, this is where the sublimation and deposition happens, right? That's what I'm trying to show you guys there with those arrows, okay? So if you're trying to read a phase diagram, identify where your different phases are on here and look at where those graphed lines are, right? And that's just gonna tell you at what temperature and at what pressure, what phase exists. That's what the point of this is, okay? Now, this is a pretty simple one. You get to some more complex things like iron. There's different forms of iron that exist at different pressures and temperatures that give different properties, conductivity and malleability, and all these kind of things that come along with it, okay? But that's all that really is coming on here, right? There's triple points, and that's just where all three phases exist in some kind of equilibrium there. So if we wanted to go back to the example that I had there previously of solid to liquid, we'd also have solid to liquid to gas, and there'd be just all three of those existing simultaneously, right? So at a specific temperature and pressure, water can exist as a solid, liquid, and a gas at the same time, right? That's what the triple point is, right? I don't know what that is off the top of my head, right? But you can look up the phase diagram for water, and you guys can figure that out. Yeah.
Why can't the liquid exist at 0 pressure?
Why can't liquid exist at 0 pressure? I mean, in this case, it can, right?
But in other cases, it could.
Could, yeah. Maybe. I can't think of an example off the top of my head. I'd imagine there's something to do with, you have to, electrons are gonna repel other electrons, right? So maybe there has to be some kind of thing that kind of keeps them together. There might be an argument for that, right?
What about supercritical fluid? What does that mean?
Yeah. So supercritical fluids are where a liquid exists, where it should be a gas, right? So you have just enough pressure. There's actually an experiment that we do, or we used to do in organic chemistry, where you can get dry ice and you just put, give you guys bad ideas to do on the weekend.
Chris, listen.
Yeah. No, you put dry ice into a vial, and dry ice will start to sublime and turn into CO2. And when it reaches a certain pressure, you'll actually see supercritical CO2 form. And if you put things like orange peels in there, like supercritical CO2 is an amazing compound. Right? That's how they decaffeinate coffee and teas and all these kind of things, right? They use supercritical CO2. And then what it does is it extracts the oils from the essential oils from the orange peels, and so then you can isolate the oils, and then you can do the organic chemistry with them as well.
So what? So the CO2 is acting almost like a magnet to organic.
No, it's a solvent, right? It's a liquid, right? Just as water, just as you guys imagine water is a liquid, you can have CO2 as a liquid at a supercritical fluid there, right? Is what it is.
Right. But then why would it have that effect on
Because of the intermolecular forces, right? It's polar, and it's got carbon, it's got oxygen, right? It's linear, it can get into things and extract it. There's a lot of different answers for that. It is super interesting. All right, anyway, so this is just the end of the slides here. This is just what I was talking about there with the critical point, which is where the supercritical fluid exists, and then the triple point where all, oh, there it is. There's the pressure and the temperature for triple point of water. Fantastic. So there it is, right? Trivia knowledge. I'm never going to ask you guys something like that, but that's okay. Okay. All right. So, let's see. We got a couple minutes here. All right. I'm going to open up my book. If you guys have your book with you.
Are we supposed to bring our books?
Are you supposed to bring the book that you? How much do you guys pay for your books? Holy crap! Really?
I got it for $70, but it was used. So.
Yeah.
But yeah. The new price is like $300 or $400.
Is it really that much? That sucks.
Yeah.
Kind of jerk professor maybe. All right. All right. So I am going to start. So I'm going to get this. So question 11.31 that's in the back of the book there. So I'll read it out to you guys here in a second when you guys get a free page or whatever it is. Oh, wait a minute, let's see if I can get this thing rolling here.
The heck is that?
Yeah, this is one of these document projectors, so in theory I should be able to show the book to you guys. In theory. Yeah, I'm betting that this is going to work. That's why I say in theory. I was right. Okay, so question 11.31. So you guys can just listen to me here. I'll tell you what the important part is. But I'll read it out and I'll tell you guys what I'm looking at. So a number of salts, right? So a number of ionic compounds contain the tetrahedral polyatomic anion, right? And I'll give you guys a formula here in a second. And other salts contain a larger anion that has a 2- charge, right? So we've got two anions, one a 1- and one a 2-. The question is why do these certain ions have a lower melting point here, right? So here's what it is. So we've got a compound that's BF4, 1-, okay? And we've got another compound that's SO4, 2-, and they have higher melting point, right? So lower melting point, higher melting point. The question is why? So what's going on to think that a BF4 with a 1- charge have a lower melting point than an SO4 with a 2- charge?
I'm assuming we're using the atomic, like the periodic table values.
Yes?
Do the identities of the atoms have something to do with it?
Do they indeed? Why would ionic compounds with BF4 have a lower melting point? Fantastic questions. See what you guys can come up with. I'd say there are a couple of good answers here. You better know.
No, it's
I like it.
Are they both tetrahedral?
Yes, they are.
Okay.
And that's important. So the book gives you that information. But that would be something good to assess in case it didn't, right? It does tell you they both have the same geometry, both tetrahedral. So what is the theme of of these chapters?
Intermolecular forces.
Intermolecular
Is it
forces.
because wait, no, oxygen is.
Oh, hang on just a minute. Okay. So The intermolecular forces, so how am I asking you to answer this? Your answer will have some kind of discussion that involves what?
Intermolecular.
Dispersion forces, right? Dipoles or hydrogen bonds. You guys got it?
Neither has hydrogen though.
I'm just giving you one component here, right? I'm telling you about the anions, right? They're saying ionic compound, right? So we're missing what the cation is.
Is the cation gonna have an impact here?
I would say maybe, right?
Do we need to figure out what the cation is?
That's impossible. Hypothetical question. Right? I'm asking you to move avocados from one side of the room to the other, right? These typical theoretical questions, right? Drawing out the Lewis structure. That's good. No, that's a great place to start, right? Great. Okay. What are dipole-dipoles?
I know hydrogen bonding is dipole-dipole.
It is a specific kind of dipole-dipole, right? So what does it mean? So magnets have poles, right? What does that mean?
Oh, permanent polarity.
Permanent, right? It's got a permanent positive or permanent negative. Permanent. Exactly, right? Exactly. What do we come up with?
Oh, you know what? They're like when you both lose another single card,
There's something very important here. Right, that versus that. What did we say about those charges? How's that gonna affect things? See what you guys can come up with here. So, have a discussion about the minuses. That could be something with it there, right? That's a good, that'd be a good avenue to approach. There's more than one right answer here, right? I mean, my answer is going to be the best, but there's other ones that would be okay too. That's all I'm saying. What do you guys think? No idea. Well, you have three ideas, right? Which are what? Dispersion, dipoles, or hydrogen bonding, right? So that would be where I would start with that, right? So whenever you're at this place where you get like stuck with something, like think about you guys know these answers. Now you haven't answered this specific question yet, but that's where you should start with this. See if you can start to make arguments from one of those three positions there. Okay? So start with dispersion. Tell me what dispersion would affect in this case. Dispersion is affected by the number of electrons, right? So count electrons. So the molecular weight.
I think it has to do with matching. Because of the subject.
The bigger.
Or it's super small, or it's going to be sulfur and or sulfur and oxygen. Compared to boron and fluorine. There it is. Because it's so small though. Well, that would be it. I mean, that's close.
Take a look at what we talked about.
That's what I got.
Where's the next one? Wherever they are. What are we thinking? It does. Cool. So there's your argument for dispersion, right? So now we've tackled one of our three forces. Let's see what you can think about that. You're a third of the way there. It's good. It's good.
Well, what is one of
No, it's great. Yeah, it's good. So what do we think?
Well, like, remember we didn't talk about this. One electron.
So we have our intermolecular force, but remember ionic is also a way that molecules talk to each other, right? So perfect, I like that. Let's see if you can come up with an argument for dispersion and dipoles and that kind of stuff also.
Bring energy into it.
I like it, drawing your Lewis structures.
bonds for it.
What do we think?
So, my feeling is
Like that.
with, the higher, like, there's a greater, like, ionic disparity for SO4, so maybe like.
What is ionic?
I'm like bigger atoms.
Okay, so here, right, so if you think about this, right, if I have a 2 minus charge, it means you're more likely to shoot electrons out, right? Because what has a negative, electrons have a negative charge, if I'm feeling negative, the negative wants to get away from another negative. However, what you're trying to say here is if I have a 2 minus charge, I'm gonna do that much more. It's gonna be harder to move a positive away from it, right? And so you're gonna have higher numbers than you're gonna have ionic charge.
Yeah.
That's great right there, right? The bigger the radius, right, we have this mismatch of size there, right? So if you take a look at the individual ions, the SO2 is a bigger.
Similar in size on the periodic table, or is there gonna be greater disparity between sizes of ions?
No, those are about the same. We're talking about the ion as a whole, right? Just sulfur's a bigger. Yes, exactly. That's what I'm saying. I'm agreeing with you there, right? So we have a change in the size of the ion. Now that's a little bit. How do I want to say this? Right? It's a good argument. Yeah, I guess that's all I'm going to say. But these are together in one column, right? That is a singular anion.
But then does it matter if, like, let's say, for argument, like, if you look at larger radius, since the boron has a larger radius than the boron.
It does, yep.
Right? So then would that affect anything?
So what's the Lewis structure of these look like? Right, and so it's basically, when you have a tetrahedral molecule, just basically think of them as a spherical shape, is kind of what it is, right? So the interior atom, the boron versus sulfur, will impact the overall shape, but not really on an individual level, so that's what it is. It's a great question, I like it. All right, so I'm seeing a lot of good answers and good thoughts from around the classroom. So who wants to venture a thought for us here then? Why, or what is one potential explanation for this observation? What could we say? Let's see. Mary, right?
Yeah.
Mary. What's one potential explanation?
Okay, so if you look at the charges, the 2 on the SO4 is higher, so that would be the higher milk.
Exactly, right? So remember we talked about ionic charges. The bigger the ionic charge, typically the higher the melting point's going to be, right? When you melt an ionic solid, we have to move the positives and the minuses away from each other, okay? So if I have a +2 versus a -2 versus a -1, right? That -2 is going to hang on to those positives a little bit more, okay? So that's a great argument to make. What else? Jill, you want to venture a guess? Not venture a guess, venture a definitively
Yeah.
correct answer. All right.
I don't know, something with like the size of the radius and how like electronegative fluorine is.
Perfect. I like that answer too, right? Taking a look at the radius of the individual atoms and the anions as a whole, right? So the individual the individual atomic radii, and then the molecule as a whole, right? Sulfur's a bigger molecule than boron is, right? And so that anion is going to have a larger radius there also, right? That might be an argument to make. I like that. What else? Yeah.
About how.
I'm sorry. Give me your name
Lizzie,
Lizzie.
or Elizabeth.
So Lizzie or Elizabeth. Okay. That's a long name for me to remember.
Can you
What-
call Lizzie?
Okay, there we go. All right, Lizzie, hit me with an answer.
I was gonna say, SO4, it weighs more atomically, so it would have more electrons, so it would have greater concentration.
Perfect, I like that answer too, right? There's an argument about dispersion forces, right? Remember, dispersion forces is an argument just of which one has more electrons in general, right? Always a good place to analyze with that. So dispersion forces, SO4 2 minus, what's the name of SO4 2 minus? Sulfate, perfect, I like it, right? So sulfate, right, has more total electrons than the BF4 does. Yeah.
Why would a bigger sulfur compared to a smaller boron make it have a higher melting point? I thought it'd be the opposite.
Aha, good observation there, right? What are we talking about with size and these kind of things? So the argument from size is something important to pay attention to. I would have to, if we wanted to make a definitive argument in this case, I would have to tell you a little bit about the cation. Because then we would say, well, if we try to match the sizes together, or how many different cations can we fit around that larger radius there? Okay.
What happens when you boil that? Would it literally that molecule would completely separate? Is that
Fantastic question. The answer is, it depends. Right? Some of these ionic compounds, they actually go into the vapor phase as the ion pairs, and some they will ionize individually. It just kind of depends on what the cation they ion are. It's actually a very active area of research. What happens in that case?
I'm sure.
Yeah. Cool. So we have an argument from dispersion. What else? What's different about oxygen there versus fluorine? Yeah.
Fluorine has a smaller atomic radius and it's much more electronegative.
Okay. So it's more electronegative, right? It's tugging away the electrons from a smaller boron there, right? We could talk about the strength of the dipoles, maybe. That would be an argument to look at also. Any other thoughts, though? Yeah. Lizzie or Elizabeth?
So fluorine is very electronegative, so I was thinking it would be the more electronegative molecule, but it's the one with the lower melting point.
Aha.
So that would make sense to me.
I love that, right? Because you're like, hey, wait a minute. I know that boron's more electronegative. And so I should think that it would have a more partial negative charge on those individual fluorines, right? That means it would have a higher dipole, which would probably make it think that it has a, what? Higher melting point, right? You guys with me on this one? You guys follow that train of thought there? But it's the exact opposite. So what does that mean? It's my second favorite answer. It's every professor's second favorite answer. It's like when we don't really know, we say, well, the ideas behind it are very complex. If you want to come to my office, I'll be happy to explain it to you. But that's honestly the truth here, right? There is no single answer that's why this happens, okay? But what you're saying is, wait a minute, I see arguments in both directions, right? That's why the question isn't asked, which of these two will have the lower melting point? It says, explain this observation. Got it? So I gave you guys some data and say, use what you know to explain that. Rationalize an idea why that might be the case. But there are arguments on both ends there, right? That's a great argument to make about fluorine as being, having a stronger dipole and all these kind of things. Okay? I like that. You guys catch me on this though? You guys see what we're looking at, right? Think about the intermolecular. Yeah, no, it's difficult, I know. But there's a couple of other great questions in the book that are very similar to this. Questions like 11.24, 11.26, and 11.27. So 11.24, 11.26, 11.27, they're all very similar to these kind of ideas here. So if you guys need a little bit more practice, or if you want to start thinking through those, right, that'd be great to kind of sit down and kind of analyze those also. Now, I think maybe, I can't remember if I said it to everybody or not, but there was one other bit of information that the book gave you here. And they told you that both of these are tetrahedral in their geometry, okay? When the book doesn't tell you what the shape is, you guys should take a look at the Lewis structure. You guys remember me talking to you guys about the ball pit at Walmart there? Different shape is gonna have different efficiency in how it can pack things around it, okay? So spherical shaped anions are gonna have typically lower melting point than some of these linear or planar compounds. So that's something to take a look at also. Okay? You guys got everything you need to know now? Yeah, we're done, Dr. H. Okay, cool. I will see you guys on Monday then, and have a good weekend.